system, there are currently on the order of 10,000 probes connected. There's a picture of one of the probes there. There are these little boxes. This RIPE Atlas has been in operation since 2011. And it's pretty widely known that due to the fact that the system is sort of put together by the RIPE NCC, there is a coverage and bias towards locations in Europe. There are also about 550 RIPE Atlas anchors, which are shown in this picture below. These are, this is like a 1U box, has a little more processing power and does a little bit more measurements. And so we'll talk a little bit about the difference between the measurements from the probes versus the anchors. So every RIPE Atlas probe and anchor performs what are called built-in measurements. And that's going to form a lot of the basis for this material. Some of those built-in measurements are, they query hostname.bind for every root server address, both over v4 and v6, and those measurement numbers are listed here. And that measurement happens every 4 minutes. And from those results, we can get round-trip times to the root servers, and we can also look at the contents that comes back from the hostname.bind query and see if we're getting an answer that would come from an actual root server. Also look a little bit at this other measurement, 30001, which is a more recent measurement, but again, it's done by all of the probes. And every 10 minutes, it sends a query for a random, a name that has a random TLD, and this is designed to measure sort of the latency to the root server system, because this query is sent to the probe's configured resolver, and then that resolver chooses which one of the root servers that it will actually forward its query to. So about data collection, the goal for this was to have one measurement per probe per root server address per day. And so in order to spread things out, the measurement times are chosen randomly for each day, and over the whole course of the interval, end up with about 300 million individual measurements. This is a sampling down by about a factor of 360 because, in fact, as I said before, this measurement happens every 4 minutes per day, and I'm just taking one of those 4-minute intervals per day. This is what the data looks like in JSON format, and there's a few fields highlighted here. You can see the first one is there's the destination address where the query was sent to. So in this case, it's for a root. There's a field which shows the results of the hostname.bind query. Here it's NNN1-LON8, representing London. And then there's a round-trip time field, or a response time field. This graph shows the number of RIPE Atlas probes over time, from 2012 to 2019, basically. And you can see that it's grown, in the early years it grew quite steadily and sort of flattened off a little bit recently at about 10,000. The top line represents the number of probes that provide IPv4 measurements, and the green is the number that provide IPv6 measurements. So obviously, a lot of the probes provide both, and it seems to be about maybe 40% of probes have both v4 and v6 connectivity. So this graph is very similar. It has a similar shape, but here there's a number of lines overlaid on each other. Each line represents the number of measurements per day for each of the root servers. This is in v4. And you can see for the most part there, all the lines line up, but there are some purple vertical bars here which represent times where seems to be data missing in the Atlas archives, or the measurements didn't happen for some reason, I'm not sure. But for the most part, it's pretty well lined up. This is for v4. For v6, it looks like this. And again, you see that you see in the purple line, there's a lot of sort of striping and spiking represent missing data. And here you can also see that for one of them, there's this sort of light blue line, which is below the top one, which represents one of the servers not having as many v6 measurements as the others. So the first thing I want to look at here is availability. So using this data to estimate availability of the root servers as we sort of are interested in that RSAC work. So most of the measurements provide a successful result, but sometimes a measurement will have an error or some kind of timeout result. And some of those error codes are shown here. What I decided to do for this was to only consider the successful measurements and the timeout measurements. So I'm kind of ignoring these other ones, which are socket errors and other sort of lookup errors and things like that. These error codes are listed in order of popularity. So other than a successful result, the most common one was a timeout 5,000, which I interpret to mean a timeout after 5,000 milliseconds or 5 seconds. So in this data, availability is the count of successful measurements divided by the count of successful and timeout measurements. This is how it looks for one individual root server operator. The purple line at the top represents IPv4, and the green line is IPv6. So the IPv4 line is right around, say, 96% maybe. The green line is about 90%. But you can see it's been quite stable over time, hasn't really changed, which I find very interesting. There's a few artifacts where maybe for one day there was some dropouts or something, but for the most part it's pretty stable. And this is how it looks for all of the individual operators, and you'll probably notice that the individual operators are not called out here, and they're sort of specified in a random order here, and that's intentional. The goal of this is not to really say one operator is doing better than the others, but just to give you a sense of the variety of things that we see from this data. And I know it's kind of small, you may want to look on the slides on your own screen, but you can see that there are some noticeable differences in each of the 13 operators here. And so this is V4 and V6 together. The top line is the V4 and the bottom line is the V6. And a natural question to ask is, why is V6 availability always so much lower than V4? Could be for a number of different reasons. Maybe there's a problem at the probe. Maybe the probe thinks it's V6 connected, but it's really not. It's trying to send the query and failing in some way. Maybe there's a problem with the V6 network. Maybe the V6 network is somehow worse than the V4 network. Or maybe there's a problem on the servers that they're not answering V6 queries as much as we think they should. So in the RIPE Atlas data, there's for each probe, they can be tagged. And one of the tags is whether V4 is working and whether V6 is working. So we can look specifically at those probes that say they have working V6 and even working V4. And we can also look specifically at the anchors. So the next couple slides are about that. This one shows all the operators, but only looking at the probes that sort of are identified as working. One little complication here is that when the probes are tagged as having working V4, that's only for sort of the current point in time. You can't go back in time and see if they were all working. So here there's still a difference between V4 and V6. Not as much, but a little bit. When we look at the probes, they're sort of much more aligned, much closer to the top and much closer to each other. This is the anchor, the results from the anchor probe sort of zoomed in, and you can see that for V4, the anchors, it's like 98, 97%, and for V6, it's 95%. I need to speed up since I'm running out of time here. For latency now, this graph shows the median latency for an individual root server over the span of time. And you can see there's some cases where some of the latencies have spiked up, but the more interesting trend is that overall there's this downward decreasing trend over time, that latency seems to be getting better. Now, it's not clear if that is due to something about the root servers. As they are more widely deployed, is that bringing latencies down? Or as the RIPE Atlas system is growing, is that resulting in lower latencies? This shows the latencies for all the operators, and here you can see quite a bit of variation, right? Note that in all of these graphs, the y-axis range is the same. It's from 0 to 200. And so some of them are higher and lower. Some of them have periods where something changes and it goes up and then it comes back down. So there's a lot of variation here. So I talked about that trend, and I wanted to sort of try to understand better what was the source of that downward trend. So I tried to come up with this idea of let's pick a subset of probes, which I would call the best probes, and these were RIPE Atlas probes that seem to be providing data over a very long period of time, and just look at those to see if you just look at those probes, do you still see this downward trend? And for the most part, you kind of do. There's, at least for some of the root server operators, you still see at least a slight increase or decrease in latency over time, even from what I would consider the best probes. Looking at the anchor probes, however, things seem to be a little bit more stable and flat. And you'll notice here that the anchor probes don't go all the way back to 2012. And I don't know if that's because they didn't exist back then, but I do have a thing in my analysis where there has to be a minimum number of probes providing data before it shows up on the graph. So that could be what that is as well. This graph compares the latency from the different sets of probes all together. So there's a purple and a green line, which are basically on top of each other at the top there. That's all the probes and the best probes. And then the anchor probes is below it, which you can see. Generally, the anchors have lower latency, probably because they're located in data centers and things like that, which have better connectivity. Okay, so again, I talked about how the hostname.bind results can let you see if queries may be intercepted. This list of responses here off to the right is from one of the servers, and so you can see actually so it's LRoot, and if it's a proper response from an LRoot server, it has this nice well-formed pattern, and we can use pattern matching to find cases where it doesn't match, and the response is coming from something other than the root server, or seems to be coming from something other than the root server. So this is how it looks for one root server operator. You can see that for IPv4, when the measurement started, the rate of interception was about 0.2%. And you see a lot of quantization artifacts there because that's because there was only maybe one or two measurements per day were showing interception. As time goes on and as the RIPE Atlas system grows in size and as more interception is happening, that quantization sort of gets smoothed out. The green line is IPv6, and not really too surprisingly, you can see that intercepting IPv6 was a little bit of an afterthought. People didn't maybe start thinking about it until 2018, and so we start to see an increase there. One thing to note here is that since both of these are trending up and to the right, that interception seems to be happening faster at a faster rate than the RIPE Atlas system is growing. This is the same data for all of the operators, and for the most part, they're all very similar in terms of interception. Not a lot of differences here. Okay, so root server system availability. This is the results from looking at the query that's designed to measure that. This query is sent to the probe's local recursive, and the results are indicate whether or not that recursive could contact one of the root servers. Here we see availability in the 98% range for all of the probes together, but the anchors, again, are much better, very, very close to 100%. Similarly, we use the same measurements to look at latency of the root server system, and that's what's shown here. There's a lot of difference here in these graphs for reasons that I'm not really sure about, and there's some strange effects, some strange sort of jumps in the data, especially in the purple line, the all probes, it jumps a couple times. And then also something strange going on with the bottom one, the anchors data, where it cuts down to 0 for some reason. This data was actually a little bit tricky to analyze. There's a lot of individual, or a lot of different results in each measurement, so this was a little bit interesting, and I'd like to explore further with folks from RIPE about why this is. So lastly, I want to finish up with a little sort of simulation that I did. Again, this is based on some questions we had in the root server system metrics work. I want to know, how many, if you had a subset of the RIPE Atlas probes, how much of the root server system do you see? So did a bunch of simulations, choosing random subsets of the 10,000 probes, and then counting how many of the root servers do you see based on those hostname.bind results. So here on this graph, on the x-axis, it's the number of Atlas probes chosen, and on the y-axis, it's the coverage. The lower line represents the minimum over a sequence of trials, and the green line represents the maximum, and so on. So if you follow this and say, well, let's say I have 100 probes or 100 sites, what percentage of the system could I expect to see? And it's something like 30%, 40% in that range. And then similarly, I'd also analyze the latency measurements along the same lines. So this shows for one of the root servers, if you take subsets of the RIPE Atlas probes and calculate the median latency, depending on which subset you get, you'll get a range from the high line to the low line. And of course, as you get more and more RIPE Atlas probes, you converge on sort of the true number. And this is how that looks for all of the individual root servers. There's, for the most part, the shape is the same. Where they end up is different, and there's some differences in the how it looks at the low end when you have a small number of probes. So just to summarize some of the results, what you get from RIPE Atlas in terms of these metrics, for root server availability, you get about 98% in v4, 95% in v6. For the root server system availability, about 98%. Median latencies for individual root servers, 25 to 50 milliseconds. For the whole system, 25 to 30 milliseconds. And currently, what we see in terms of interception of queries is about just under 1%. So that's it. Time for questions.
Interesting. I had looked at some of the same things, so I was going to ask you. You were talking about some of the probes cannot reach certain root servers. How much is the overlap in that, i.e. how many root servers each probe can reach? Is it the ones that can't reach, are they all the same, or are the selective ones they can't reach?
So I don't have any data on that, but there was of course a well-known case which was recently on the mailing list about why one root server in particular is unreachable over v6, right?
Yes.
So that shows up very, very clearly here.
Yeah.
But to your more general question, I don't have
You didn't
any
look
data.
at it.
But we could. I mean,
Yeah.
from the data I have, it'd be pretty easy to generate some
Yeah,
graphs.
so
like that.
I would like to see if that
Okay.
also correlates with the interception.
Yeah, my feeling is that it's mostly individual timeouts at play here. It's not the fact that one is cut off, but we might be able to find cases where, there is something more serious.
Brian Dixon, GoDaddy. I have a hypothesis that at least some of the interception is due to local root instances, whatever that RFC is. Did you look at the probes that are seeing the intercepts and then looking at the latency they're experiencing towards each of the root servers and see if that jumps out?
So I did look at it. It's not here in the presentation, but I did look at that. Yeah, definitely in the cases where there's interception, the latency is lower. And in fact, I maybe should have clarified, in the latency graphs that I presented here, those intercepted queries were not, they were excluded. Right?
Okay.
So their latencies were not represented in that data.
Okay.
Because they are very low. Yeah.
Okay.
Yeah.
Thanks.
Shinta Sato from JPRS. So the RIPE Atlas is very concentrated in the RIPE region for the place of the vantage point. So if you equally distribute the point in the worldwide, will this latency or some of those kind of things change, you think?
I think it would, yeah. And that would be actually, I think, something we could do because there are so many Atlas probes, it would be pretty easy to find a subset that represented sort of whatever geographic distribution you thought was correct. I mean, so the hard part there is finding, determining what's the correct representation. But
Okay.
yeah, since there's so many probes, you could find subsets that, and
Like
we
to
can do
see
that too. Yeah.
Those kind of things. as
Yeah,
well.
absolutely.
Hey, Dan Mahoney from ISC. Early on your slide deck, you had said that there was a question that you asked of the roots where you query a random top-level domain. Is that an existing domain, or are you just picking something that should exist at the APAC and seeing if it comes back?
Right. So in that measurement, there's a query,
Right.
and it's got many labels, right? But the final label, the top label, consists of random characters. It's like a 10-letter random string. So it's designed to not exist in the root zone.
Okay, so it could be QZ or XX or whatever, not just here's what I know to be in the root and.
Right.
Okay.
Right. It's chosen at random every time the query is generated, and so the idea is that it should not be cached and it should not
Right.
exist in the root. Now, NSEC caching, which Jeff talked about, and that could affect these measurements,
Right.
but for now we assume they're not affecting the measurements.
Yeah, your talk wasn't specific about whether it was or wasn't. Okay, thank you.
Yeah.
Hi, Dwayne. We have a question from the Jabber room from Mauricio.
Exciting.
So Jabber still works, all of 4, by the way. Question for Dwayne. About the interception, besides the change in the text hostname record, does this measurement see any other changes in the SOA record or any other value?
So in these measurements that I did, the SOA data is not provided. Now there may be other ripe atlas measurements that do query for the SOA record. I did not look at those. So that would be a way to confirm if this is true interception or not. Yeah, I don't. So the answer is I don't know.
We have a couple more minutes for questions, so if you have some more. If not, I would thank Dwayne for a nice presentation. And as our speakers are changing, I would remind you to fill in the surveys. We haven't received too many submissions yet, and you can already do that for the presentations that finished. Our next speaker is Wes Hardaker again, and he will talk on the topic of what's in a name.
I can take Dwayne's remaining time, that's fine. So I'm Wes Hardaker, and today I wanted to talk about actually some work that a master's student intern at USC did, started a year ago, a little over a year and a half ago actually, and some results. I'm going to go through a ridiculous number of graphs, not many answers, lots of questions, don't blink. So let's start with diddle data. So this is diddle data from 2018. It's just the diddle data that USC ISI generated, not all of them. The question is, what is all of this stuff? So I gave it to her as an exercise to sort of look through all this stuff and break down things in a number of ways. And the one I gave her up leading, that I figured it would take her all summer to finish, was, tell me how much of that's Chrome, how much of the data is Chrome. She did that in 2 weeks, so we went on to do a whole bunch of other stuff. So Chrome, I assume most of you know, are Chromium-based products. They generate 3 randomly generated and thus likely non-existent host names when they start up or during network detection. And they do this to check NX domain hijacking. Basically, are you behind a paywall or not, or something else nefarious. So they do this by, in the C code, this is what you can actually go look at, or C++ code. They generate some random ints between a random int in length between 7 and 15 characters in length between letters A to Z. So basically, they're generating garbage queries from A to Z and 7 to 15 in length. So the question is, how much of that actually ends up at the root? Because all garbage names end up at the root. So this is the histogram how you generated for the number of entries in the root zone at that time that have 2 letters versus 3 letters versus 4 or whatever. And you can see there's diminishing returns, and there's one out there that's 24 long. I don't remember what it is, but clearly all the things like the country code CCTLDs are on the left-hand bar. The question is, what does the traffic look like? The traffic looks quite different. So the traffic has these, weird patterns in it, and you can see that, the one label queries at the far left are probably dot. Chrome is all in that middle bar. So in that 2 days of diddle data, Chrome is generating the most of it. Those are between 7 and 15. That bar to the left is 3 and 4, which are things like ComNet and org, and I suspect that most of the 4th one is probably ARPA, for example. The CCTLDs are that far bar left to the left. So if next we started to look at other ways to break things down. So the top label in this one is the total number, is this total amount of traffic. So it's the same graph that you saw earlier. The dark blue line, so the 3rd one down, is everything that is a single label request only. In other words, only a single label, no dots, essentially, unless you count the last dot. The orange one is, I didn't regenerate this graph, some of the rest of them are better. The orange one is for multi-labels. So the orange one is things that at least has 1 dot somewhere in it or multiple labels. So you can see that multiple labels tends to dwarf the 1 labels. The red line on the very bottom, that very bottom line, is something that exactly matched a root name. So you can see that the number of requests that are exactly matching a root name are quite low. So if we just look at the single labels, we just dive into only single label traffic. The blue line is only the single label traffic at the top. The second line underneath, the light blue line, is all Chrome. So you can see that the vast majority of traffic received that are single labels is coming mostly from Chrome. The bottom 2 labels are 2 things. They actually almost exactly overlap, which is one is the root name data, so it's actually a query that actually is in the root name itself. The second one is she ran some language detection on it to determine what sort of language it is. So if it was determined to be a language, that ended up in the other line. Everything else is in that orange line, so all the undefined stuff is in the orange line that's sort of flat with some spikes. Then she broke down things by common languages. So there's a couple of Python libraries that she used to send these single label domains through and say, what is it? The top one is sort of the root names. And it's hard to dive into these. You can zoom into them if you download the presentation. But basically, there's German, English, French, and a whole bunch of languages, and you can look. And they are mostly synonymous. And I think a lot of that occurs because a lot of words exist in multiple languages at once. I actually had her zoom in and then send it through a different algorithm that basically you give it, and this algorithm is really expecting a sentence, but we just gave it single words, so we confused it. But if you give it just a single word and you say, tell me what language that is, to your best of your knowledge, what is it? So I don't know if you can see, but that very top line is Polish. So it turns out that most of the internet speaks Polish. Clearly that's not true. And so when I explained to her, did you look at the words that were actually being classified as Polish? Chrome classifies mostly as Polish with the random words. So clearly I take this as the Polish version of the Polish text that was fed into that algorithm was probably less robust than the rest of the languages. Because Maltese is also quite high, by the way. Anyway, so there's a lot of future work that could be done on the language side of things. The first thing you do is you eliminate things that are garbage, and you eliminate things like underbar LDAP and other stuff that clearly aren't a language. So then I had her break down, well, let's look at the multi-label stuff. She really wanted to go into this, and I said, I don't know that we'll get to it by the end of summer. She started it at the end of summer, and I kept her on for another 3 months because she was making such good progress. So as a reminder, this is what the total traffic looks like. This is what the traffic with just a single label looks like. And so you can actually see that there, if I shift back and forth, there's a complete waveform shift. So you can see that as we start breaking things down by the number of labels, you get interesting variations. So we're going to dive into that quite a bit. So this is all the labels from 1 to 6. So everything from 1 to 6 labels long. So www.example.com is 3 labels if you don't understand that. Interestingly enough, a single label occurs more frequently than a 3 label, which occurs more frequently than a 4 label, which occurs more frequently than a 2 label. So the numbering there is interesting. if you look at just the 2s and the 3s, so just the 2 label and the 3 labels, there's a weird waveform on the left. What is all that mess? What caused that huge spike over there? So to try and figure that out, it was actually harder because it's actually spread quite widely, and in looking at the data, it's actually sort of hard to look at. So what I ended up doing was, and this is actually just last week, I took sort of the top 25 right-handed 2 labels inside and outside that event block, and I graphed them both. So during the event is the green lower ones, and after the event, so after that weird block shape kind of ended, is the purple ones. And what you'll notice is that there's a whole bunch that only existed during it. They were rare, TLDs that were being used. So I decided to just go look at those. So that should be pretty much only the questionable traffic. And it turned out to be probably a dynamic generation algorithm type name, very similar to the study that Infoblox did, where, again, as I mentioned at the microphone earlier, there's a lot of random words strung together. Probably it's a command and control type server. And this is becoming more and more common, as well as there's some random other names in there as well. Further work is being done on that type of work. More details in San Francisco or some later. If we look at all of the graphs going from 5 to 12 labels in length, there's lots of stuff. And I'm going to dive into those a little bit more frequently. If you look at 6 and 7, everybody knows why 6 was afraid of 7, right? 6 and 7 are fairly flat. They look, there's a little bit of interesting stuff in them. If you look at 8 and 9, there's all of a sudden these massive spikes that are clearly, something algorithmic. Humans don't make these sudden spikes like that. That's coming from something or other. So if you look into Y, I looked at 100,000 random domains coming from lengths 8 and 9, and most of it was the ending label was openstacklocal with 34,000 things out of 100,000 being being openstacklocal. .local was next, and .local domain was after that. And you can see that most of those ending suffixes are not actually in the root. Looking at just the openstacklocal stuff, which turned out to be the majority of it, you can see that it all looks like anti-spam type related stuff, and 99.7 of those were from one ASN. So somebody has a very messed up anti-spam phishing thing probably in their VM system. As I said, I'm going to generate a lot of questions. I didn't have much ground truth for what's actually going on because I didn't reach out and contact anybody. Looking strangely into the other waveforms, this is 11 labels, weird sort of patterns going on there. 14 labels actually shows something similar. I did not dive into those. The 20 labels have these sudden spikes in them. All of a sudden these queries of at least 20 labels long. If you look into those, you'll find that some of them make sense, like things in .ARPA happen to have a very long and very frequent length. They make perfect sense. Other ones are, data leaks and other mistakes. My favorite is the first one, which is, a .rpm file, which was clearly put into the DNS as a full query. Lots of stuff ending in .lan for some reason. Lots of repeated prefixes, things like www endlessly. Looking at 23 labels, again, more strange spikes, lots of flat background noise of probably regular stuff, and then some sudden spikes. 80% of that was from one domain. I'd like to know what they're doing there, because they're clearly doing some sort of database, distributed database kind of lookup system with lots of serial number-like looking stuff in it. Didn't ask them. As you keep going longer, this stuff goes on forever, well, until you hit the label cap, right? So this is sort of the longer and longer you get to more and more random low-length stuff. Now we're getting to query counts of 4 and 8 and up to 14 for 41 to 47 type lengths, 39 to 47. You can keep going higher, so 66 to 82. There's still a lot of stuff in that stuff, and they're just random spikes. And I apologize; those should really be impulse spikes, not triangles. And then there's some very late ones that suddenly got this spike. So if you look at the last one, the label counts are only up to 25. But if you pull out some of the later ones that have sudden spikiness, that right-hand spike has actually most of those numbers. So something's going on there where and I didn't dive into that, where a lot of stuff is querying very, very long stuff in a sudden burst. All the way up from 103 to 122, which is sort of the end of the line, you still get some random stuff way out that far. If you look at some of these oddballs, to sort of conclude, there's really weird stuff out that far. This is in the very deep end of the DNS where only demons lie. This one I found fascinating. Lots of control characters that are control ones essentially. Note that there's a \3 in there. It starts with a 25. There's an A somewhere in the middle, and the highlighted ones on the bottom don't have a dot in the middle, so that's a single label of a whole bunch of ones. I can't explain that one. So that was, by the way, that was 67% of those longer traffic was this type of stuff. There's a bunch of it. Thank you for pronouncing that for me. I was wondering how to do that. 28% looked like this type of stuff, lots of M's in the front. Note that there are sort of real domain names buried in there and a common suffix after it, but you can see that it ends in .com, so that's probably some sort of buffer overflow, or they forgot the length the length they put into the packet didn't match the length they actually wanted to query. 4% was things that looked like this. And so this one caught my eye. Anybody guess? Any guesses what this might be? If you look at all those numbers, they're ASCII, right? Those are all within the ASCII range. And yeah, I'm about done. So 66 of these look things like this. I removed the IP addresses of these, but they were SOAP-related URL suffixes with a misleading first character that was strange. How these leaked to the DNS, I really have no idea. How they got encoded as dotted ASCII numbers, I have no idea. Fascinating how many mistakes exist in the DNS. So future, lots of bad stuff. We all knew that. Lots of leakage. We all knew that. We need better, there's a lot of better classification work that could be done there, as well as temporal patterning of why there's rapid spikes and then going away, and what people are doing deep in the bowels of the DNS that you don't want to dive into. And then, of course, language, as I mentioned earlier. Any questions?
Brian Hartvickson, Cisco. No question, just to comment the Sophos XSL stuff. That's antivirus lookups, where it's trying to get a categorization on a file that it doesn't already know. So yes, it actually does include subscription information, basically, like an ID, a hash that they need to authorize. So,
right. Okay. Thank you.
Petr Špaček, CZNet. Thank you for doing that. The longer I look into DNS data, the more I'm amazed that it actually works still. Anyway, I will add more information about the antiviruses, because McAfee is doing the same crap.
Yeah.
ESET is doing the same crap, and I suspect, I forgot some other names, but we have seen like super long names on servers which break if you do 0x20 randomization and stuff like that. So antiviruses do
my colleagues and I might come back at some point, because there's a ton of stuff like this, and we'd really like to be able to classify the ways that people are using DNS. And this is just the beginning of the tip of the iceberg. And yeah, there's a lot of distributed database-like stuff being used. So.
Yeah, it would be super awesome if you can automate some of these analyses, so you can run it like every day or something and find out, okay, this is new botnet doing, its DGA algorithm all over the place.
We're standing up infrastructure to do that right now.
Excellent, thank you.
Okay. All right, thank you.
Thank you, Wes. So our next speaker is Mr. Yoshiro Yonea from JPRS, and he will talk on the topic of towards detecting DNSSEC validation failure with passive measurements at TLD DNS servers. And please don't forget to fill the surveys.
Hi, this is Yoshiro Yone from JPRS. Today, I explain about our research work regarding to how to detect DNSSEC validation failure at the TLD DNS server. So, as you know, DNSSEC validation failures happens frequently still. So, but the reliability of operation is a key of DNSSEC deployment. So that we started this research work. And our research question is, how can we detect validation failure rapidly and efficiently? The one way is using active measurement to the DNS resolvers, the validators. So periodic querying to authoritative servers can find the DNSSEC validation failure, but it causes a high load to the authoritative servers. So we are thinking about how can we detect through the passive measurement. That means the changes of query patterns could be a good indicator for finding the DNSSEC validation failure. So towards the detecting validation failures, we set some measurement environment. The goal of this measurement is detecting change of query patterns at ccTLD DNS servers before and after the failure. And the current our work, we are analyzing with active, in conjunction with active measurement. We are using LIPE Atlas probe as a DNS client and use about 500 or more DNSSEC validators in ISP or edges. But we carefully excluded public DNS because it's matters, it will change the patterns. So I will explain how we find the public DNS. And we set up local authoritative DNS servers at 3-level domain. So that sets the success, both successful and failure of DNSSEC validation. And also we set several TTLs for NS, DS, DNS key records. And passive measurement vantage points are JPDNS TLD servers. This figure shows the measurement overview. So we use LIPE Atlas probe and local authoritative as an active measurement point, and we use JPDNS as a passive measurement point. And in this research, we used the the PCAP data at the JPDNS in the period of April 2018. That was the same time at DITL 2018. And we used NS, A DNS key, and NS record to the active measurement local authoritative servers. This figure shows how we find the public DNS servers. So prior to this measurement, we sent some tagged query to our local authoritative servers. And we match the log of LIPE Atlas and the authoritative server and find if the same tag comes from different IP addresses. And such resolvers, we thought that it would be a public DNS. So we excluded such public server. And for the TTL setting of NS and DNS key, also prior to our measurement, we checked the TTL setting of existing JP, famous JP domain names, and we found some categories of the TTL settings. So this quadrant shows the NS TTL and DNS TTL of the short or long. So some of them, especially media sites, uses both short TTLs, and some governmental organizations use the long, short NS, but the long DNS key, like that. There is no guidance of this kind of settings, but this classification is funny. So according to this prior measurement, we set these parameters for the several zones. We prepared 8 zones for various TTL settings. So there are mainly 2 categories for the successful validators and failed validators, and each NS and DNS key are 600 or 7200 second. And for the measurement, live address probe send queries in interval of 540 seconds, and the queries sent in the duration of 8100 seconds. And this table shows the result of queries to the local authoritative servers. Local authoritative is at the 3rd level. So overall queries increased in failures as expected. And we found that the TTL setting for NS and DNS key worked in successful validator. And this table shows the queries observed at the CCTLD or JPDNS level. So we see still increased, but not significant amount of the queries. And we found that DNS key is better indicator than DS. And longer DNS key TTL is better than the shorter DNS key, because we think it is due to the negative cache effect. So as you see, for example, the query to the DNS key increases in the longer TTL. NG, for example, NG43 uses the longer DNS key TTL, so the increasing ratio is higher than the shorter DNS key TTL. And this table shows the attenuation at local authoritative server and the CCTLD DPDNS server level. As you see, the total queries are very different, but we can see the attenuation of failure DNS key queries is still about the same ratio. So we thought that the DNS key increasing DNS key is a kind of indicator of DNSSEC validation failure. But as you see, the validation failure in minor domains is likely difficult to detect because these domains are referred very small number in a small number or not so frequently. So the conclusion, we conducted DNS passive and active measurement to know query behaviors in DNSSEC failures. And we found DNS queries increased at DNSSEC validation failure. But as you see, attenuation of queries in DNS hierarchy very differ. And the DNS key difference is still a good metric to detect validation failure. Also, DS is not so significant to detect the failure. And the future work. So we have a lot of things, but today I'd like to hear from you about how we can improve our research work. And our main goal from the operational point of view is how can we effectively find it is a real-time or quasi-real-time detection method at the TLD server side. Thank you.
Victor Hoffney. Can you talk about which TLDs you're measuring and how many domains you're covering?
Yes, we measured JP.
Just JP?
Just JP, because we are .jp registry.
Okay.
So
and how many signed domains do you have in JP?
At this moment, we only have about 500 or so. Not so many, very small number. And at this measurement, we used our crafted domain name to check the failure status and the successful status. I will show you the setting.
Okay. So the goal isn't so much to learn about how many domains are working or not, as to see whether you can detect this through the TLD, right? Because you can 500 domains, in a fraction of a second in parallel, you could get all the data as to whether they're working or not, without making indirect measurements, right? You can just directly measure them all. Yes.
Yes, it's possible. Possibly not 500 is possible to measure each domain, but we'd like to know. Not using such measurement method, because I cannot predict the future, but I hope the DNSSEC deployment in Japan getting higher.
Right, because I'm doing 10 million domains a day. It takes 5 hours on my little machine at home to do 10 million domains a day. So you have a few orders of magnitude to go and still be able to do direct measurements without having to guess. Of those 10 million, by the way, about 100,000 are either lame or bogus. That kind of gives you a scale of worldwide what the story is. There's lots of parked domains that nobody cares whether the DNSSEC works or not. So various ways it fails for a small fraction, but 1 in 100 is broken.
Thank you.
So this is Andre, I see. I actually, like Victor, almost took it away from me. So what I'm missing from your talk and from your research, what is your motivation? Do you plan to act upon if you detect the validation failures in your data, do you, like somebody will come and look at it, or do you plan to integrate it as monitoring in the zone? So what's the motivation behind the research?
Our motivation is to find the DNSSEC failure phenomenon in TLD servers, because we are always monitoring our TLD servers. So if we can find some DNSSEC abnormal status in our server, then we can contact to the ISPs or registrars about some bad thing is happening. And that kind of warning or notification should become from some authority. Japanese people think that that kind of notification from the some authorities is reliable. But if it came from the end users, then the operators or customer support people is
Okay.
Was to find.
Don't get me wrong. I find fascinating, but I just didn't know what do you plan to do with it. So you will use it on operations of the JP domain. Okay, thanks.
Victor again. Yeah, I want to comment that there's a vast range of problem rates in various TLDs. Some have extremely low rates of bogus or DNSSEC breakage, Brazil is pretty much at the top at 99.96% of their DNSSEC domains working. And the reason for that is they do active monitoring and notification and taking care that the breakage is acted upon and resolved. On the low end, at the moment, Australia is at 85% or so working, so nobody's looking at all, and there's a fair number of broken domains. So yes, please monitor and intervene, and that'll be maybe you'll get to 99.9 something %. That'd be great.
Okay, thank you.
Ralphie, welcome. Thanks a lot for doing this. So while we were in the question section, I was wondering, could you also use that to kind of find out broken validators?
No, in this measurement, we don't find the failing or
yeah.
broken
I
validators.
mean, going forward, I think your attention is to. I mean, these were domains you prepared in the measurement, but I think your goal going forward will be to find stuff you didn't prepare, and that's where I was thinking: could we also find bogus validators using that technology?
So, yeah, the finding validator is not current our research work.
Okay.
Thank you again for the presentation. Thank you for answering the questions. Please fill in the surveys. And our last presentation is by Casey DCO from BYU. And the title of the talk is on DNSSEC negative responses, lies, and zone size detection.
All right. Yes, my presentation is being repaired. Cannot read 0. Okay. Worst case, we can do the PDF if we have to. It's just there's some animations that were better to do with it, so we'll do without. All right. Hello, everyone. I'm Casey DCO from Brigham Young University. And the title of this is on DNSSEC negative responses, lies, and zone size detection. I also could have called this talk Fun with NSEC 3, but I chose not to. So, and we'll see why in a little bit. So the DNS, we can think of the DNS sometimes in the way that we might picture it as an open book, in the sense that it's a query response protocol. We translate the name to IP address. And so we could do a lot of guessing and just say, hey, what names are out there by querying? And it will tell us yes or no. But it does require guess and check to be able to do that. There's no general way to say, hey, for example, what are all the names underneath .com? Now, you might ask, what are the practical reasons for that? Well, there might be a number of reasons why you want to know what names are in a given DNS zone. I'm not going to go through a lot of that today, but in general, in a privacy-centric world, we might be asking the questions, how much do we really want other people to know about our configuration? Or in other words, how much do we not want them to know about our configuration? So some of this will apply to that, to those questions, but there might be more abstract questions, just simply how might we measure different aspects of the domain name system in terms of what sizes are DNS zones. And so the research I'm going to talk about today will take some of these principles that are displayed here and try and put those into practice. Okay, so with DNSSEC, this is hard without the animations, but we'll do it. Let's see. Okay, we'll do our best here. So the idea is that we have these, when you ask a question for something that does not exist, then in the case of signing with NSEC, we have a list of names that do exist, and then those names form a chain when you put them in canonical ordering. So when you query something, the authoritative server will simply say, hey, what name is in here that where would the name fall if it did exist, and then it would send those two names, which you would see in my beautiful animation if it were here. But what you're able to see then in the end is the surrounding names for that. So in this case, we have example, apple, car, and if you were to ask for banana, it would fall between apple and car, and you would be able to see the apple and car do exist, and then you could actually do this all the way down and learn everything in a given zone. And this has been done. This has actually been around for quite a while and been known, and in fact, Eric Osterweil did this as part of his PhD dissertation many years ago with SecSpider. Okay. So then we had something later come around called NSEC3, and instead of forming a chain of the names of a given zone, we have a chain of the hashes of the names. Okay, so in my contrived list of hashes over here, if you were to query something, you'd say, okay, bar.example.com hashes to such and such name over here, EP02, whatever, and then you would say, okay, what hashes does this fall between? And so the server would send back the hashes of the names, the hashes between which the hash of the queried name falls in between. Okay, so you're revealing a little bit less, but there has been some work done to show that with a handful of these hashes, you can actually use GPUs to break these hashes in a relatively short period of time. So you're not actually hiding that much by using NSEC3, but maybe from the casual observer. Not many humans can decode NSEC3 with your eyes, but there's one actually. So okay, so we'll keep going. So later on, we hear about something called white lies. That's the kind of colloquial term for it. But the idea behind that is the server is actually generating the NSEC3 records on the fly. So rather than having a pre-existing, like the previous slide shows kind of this pre-existing list of hashes of names in the zone, here we now generate that list on the fly. Okay, excuse me, not the list on the fly, but the two enclosing names on the fly, depending on what the hash of the query name is. Now, the difficulty with that is just the fact that the server now has to generate also a signature on the fly. Otherwise, it's just fine. And it works for many, many configurations, but we call that white lies in the NSEC3 world. Something comparable, mostly implemented by Cloudflare, is something that's been called black lies. Okay, it's a play on the term white lies. But the idea is to produce a minimal covering using NSEC instead of NSEC3. So instead of showing two hashes, one on either side of the hash of the query name, we're generating two, actually the name itself, whatever was queried. Again, this is on the fly. And then the next name is a kind of a minimal covering name. And so instead of sending a response that, hey, this name doesn't exist, you say it does exist, but there's nothing after it, and there are also no records associated with it. Okay, so this is a way of, again, on the fly, kind of saying, hey, this doesn't exist, but without revealing anything. Okay, so we have kind of these four general mechanisms: NSEC, NSEC3, white lies, and black lies. Now, last year, it was early last year, we actually took from 821, let's see, we had the zone files for 821 top-level domains that came from various sources. And so we extracted the second-level domains from those zone files. So we were able to analyze about 2.2, from those total zones, we found about 2.2 million DNSSEC signed zones. And then we classified them using these categories that I just mentioned. So we had traditional NSEC, traditional NSEC3, NSEC3 with white lies, and NSEC with black lies. Okay, that's kind of a tongue twister. Then we had some in the category of unclassified because they weren't sending us the right records. We couldn't tell what they were based on the responses we were getting back. So we had about 2.2 million. You can see here that the largest category was traditional NSEC3, followed by white lies, NSEC3, followed by traditional NSEC. Okay, and then there was about 48,000 with black lies and about 66,000 unclassified. Okay, so that's kind of the breakdown that we had. But now let's take this a bit further and see what could we do that's somewhat novel with this, with the data that we found. Okay, so we've talked about the idea of using these kind of non-existent query names to learn and walk through the entire contents of the zone using NSEC3 and doing something similar, using NSEC and doing something similar with the GPU computation to learn something about NSEC3 signed zones. But what about, can we use a minimal number of queries to learn the size of an NSEC3 signed DNS zone? And so that's what the rest of this research focuses on. So here's the analogy. If we take a pie, and I know it's getting towards lunchtime, so I know all of you can visualize food, okay? So if we think about pie slices and we say, okay, if I show you this slice of pie, and then I say, okay, how many people were there for dinner? If a single pie slice was this big, well, you'd all intuitively say 3, right? Just kidding, 4, okay. Just making sure you're awake. All right, so 4, right? Because you'd say, hey, that's obviously a quarter of the pie, and so you can say there were 4 people there. Okay, and what we're doing inside our minds is just saying, okay, there's 360 degrees total in the pie, so if we divide it by the angle of the slice that we saw, then we get 360 divided by 90, and that's 4 slices, okay? Now, if we think about this in terms of hash space, okay, instead of 360 degrees, what we have is a hash space of 2 to the 160, which is the NSEC3 hash space, okay? You have 160 bits, so 2 to the 160 possible combinations, okay? And then if you look at on the upper left-hand corner here, what you have is what we call a hash distance between an owner name and the hash space, the next hash in an NSEC3 record. So that's what we call our distance, okay, when we subtract one from the other. Okay, and then the lines, kind of the radii coming out, those are what we call the actual NSEC3 hashes in there, okay? So that's how we break things down in terms of applying the same pie analogy, but in NSEC3. So the question is it as easy as simply dividing the total hash space by a distance for a given response? Well, it turns out it's not, because not all the distances are equal. There's some sort of a distribution. So we need a sample to go along with it, okay? So first of all, we wanted to see, now this is kind of a dense slide here, but I want you to, I'll tell you about what the experiment is that we conducted. First, we just said, okay, take a bunch of names and create an NSEC3 hash for them, and then see how well distributed across the hash space were the hashes that came out of these NSEC3 hash names. And what we found was that it was a very, very uniform distribution. So what you're seeing here is on the right is the distribution of those hash names across these bins. And what this is showing is the number of hashes per bin in that hash space. So we divided it up into 1,024 equal-sized bins, this hash space, and then said how many are in there. And then this is the graph that shows that. And so this is this follows a normal distribution, which shows that they're uniformly distributed. So okay, the hashes are uniformly distributed across the hash space. So let's try our analysis and see if it works. So what we did, sorry, I wish this were animated so you didn't have to see the thumbs down already. But the point is, what we did was with a test zone, we generated 10,000 randomly generated names, and we signed it with NSEC3. And then we selected 20 NSEC3 records by doing 18 queries. And the reason why that works is because two of the NSEC3 records are going to be somewhat consistent in all your responses, so it only takes 18 queries to get 20 NSEC3 records. I'm not going to go into the details of why that is, but just trust me on that. Okay, so we ended up with 20 NSEC3 records, and then we did this 1,000 times, okay, for this given zone. And then, so we wanted to see how successful we were. What we came up with, this is our error over here in terms of a percentage. We wanted that error to be around 0, but it turns out the median was around 50% off, okay? So not great. And so we had to ask the question, what in the world are we doing wrong? Well, it turns out that we were measuring the distribution of NSEC3 hashes when we looked earlier, and those are uniformly distributed, but we were not measuring the distribution of the NSEC3 distances, which is what we really care about. Because remember, we were looking at the size of that pie slice, not where the lines were on the pie. So it really depended on looking at the distance. So it turns out that distances are distributed differently. Okay, if you look at this is on the right hand. I'm actually going to skip to the next slide so it'll show you a little bit better. What we're looking at, if we go back to this analogy, is it turns out that the representation of distances in there is such that you have several distances, a small number of distances that take up a large amount of the hash space. So in this case, if I were to throw a dart at this pi, there's a much greater probability that I would hit one of those two big pink areas, right? Except the problem is those are not representative of the rest of the hashes or the rest of the distances in that pi, because they take up about 50%, whereas there are 7 other slices in there or so that are much more representative of what the distances are like, but they're much less likely to be hit. Okay, and that's what it's like when we break down the hash space as well. It turns out that this is an exponential distribution following a Poisson process. And so if you look at the graph on the right, what this is showing is kind of the breakdown of the number of hashes in a given fraction of the hash space, and specifically that 50% of all the distances in a given DNS zone comprise only 15% of the hash space. So it looks very much like kind of this pie that I just showed you, okay? And so what we had to do to account for this, and by the way, this is independent of zone size. So any zone, whatever size, it always followed this distribution, which is actually really nice because then all we had to do was say, okay, well, let's map that distribution. And what we can do is apply a weight corresponding. So we broke this down into 10 different groupings here. And so for each grouping of 10%, or a decile, it corresponds to the fraction, the weight corresponds to the fraction of NSEC records in that space. So that way we can apply this weight and say, hey, everything in the first 10 percentile is a larger weight. So even though we may only see it once, the chance of it hitting that one are much less. We apply much greater weight so it pulls it up in the average rather than just doing a kind of a normal average. Okay, and when we do that, we do much better in terms of we rerun our test of only taking 18 queries to a given zone, and then we basically divide up, we sort these distances and say, okay, apply this weight to the one on the far left, and then and so on down the line. And so, so when we do that and take that weighted average, it turns out it's much, much better in terms of error. And so we were much closer to our target. Now, finally, I'm going to get to the part where we actually measured some real zones in the wild, having tested our experimentation here. And what we found when we measured all these NSEC 3 zones, traditional NSEC 3 that were about 53% of the DNSSEC signed zones that we found, that about 90% of them have 10 names or fewer in the zone. Okay, so quite small. 99% of zones have 40 names or fewer in this set that we had. And then there are about 1% that reached up to about 4 million. So, so really interesting kind of long tail view of zone size that we were able to apply once we had kind of honed in our methodology using NSEC 3 to determine zone size. Okay, so just in summary, DNSSEC provides origin authentication, and we have NSEC and NSEC 3 to provide authenticated denial of existence. And there are some obfuscation solutions that I mentioned, white lies and black lies. They each have their own challenges. But using NSEC 3 and using this kind of uniform hash space, we can actually check the size of NSEC 3 signed zones with a relatively small number of queries. And thank you. Any questions?
Brian Dixon, GoDaddy. So I would conclude from that in the reverse sense that zones that have 40 or fewer names, there's literally no real good reason for doing NSEC 3 because there isn't any stuff to protect because you can enumerate those trivially other than the actual names themselves, but those are going to be coming out of legitimate queries. So that's very interesting data. Did you categorize the zones themselves in that top 1% as far as TLD or effective TLD versus SLD?
We have not, and actually that's a great point. That's kind of something we left to future work that we wanted to look at. And there's a bunch of other places there. I mean, we've got government mandated DNSSEC deployment and all sorts of categories, right? Free DNSSEC deployment. I mean, and so that would be another category we'd love to look at.
Cool.
Yeah.
Thanks.
Thanks.
But that's
Thanks,
great work.
Brian. Yeah.
All over from Cloudflare. Casey, I like that. You're a better mathematician than me. I tried to do this before and failed. Question. When you issued your 18 queries, did you use the results of prior ones to suppress queries?
No, we did not, because we actually, so the question was, did we toss out or make sure we got new results? And we didn't, because we wanted random selection with replacement.
Okay.
Yeah, that's the way it worked statistically speaking. We had to have the with replacement to make it work. And in fact, in the case of small size zones, that's the only way it could work, is to do that.
Okay.
So in fact, I didn't mention this, but in the case of the really small zones, we almost always enumerated all of them for the really small size zones, which meant that we didn't really need our method, but that really helped for the larger size zones that we were doing.
The other point that I would add to that one is for all the smaller zones, whenever a name is added or deleted, it's very obvious.
That's true. Yeah, thank you, Oliver.
Hi, this is Martin from SIDN. Thank you for this work, very interesting. A few years ago, Bert Hubert from PowerDNS presented similar work, and he used something called hyperloglog. Are you aware of this work, and how does it compare to your results? Are they similar, or?
Yeah, thank you so much for bringing that up. And actually, apologies. Sorry, I'll say just a little bit of information about this. I didn't know about this actually until I presented this, and the PC told me, "Did you know about this?" And I didn't. And I apologize actually to Bert and Company for not actually referencing that on my slides. That was my fault. But just to say some of the differences, so a couple things. The trick that we came across, where back here you saw that we had not used the weighted. We weren't using the weighted average. That was actually a shortcoming in, at least that I had noticed from the previous slides. I didn't see the presentation. From what I saw, this would have come into play. So that's one of the reasons we were measuring error, to see how close we actually were. It wasn't clear to me that this was being done. But it would have come to bite, and you would have been off almost 50%. But again, I didn't see the presentation, so I can't speak authoritatively on that. The second thing is that Bert had applied it towards looking at signed domains within top-level domains, whereas we were looking at zone sizes in general at second-level domains and below, if that makes sense. So the application was a little bit different as well. Yeah, and the methodology was slightly different. We were using our own tool, but in general, yeah, there was a lot of overlap in the general idea.
Okay, thanks.
Thank you so much. All right, thank you very much.
So that was all for the presentations. Please fill in the surveys. I know I'm a little annoying with that, but we really need your feedback. And there's a demo booth still outside the room, so you will find Jerry there. Please visit it. And now I will just hand this over to Keith because he has some announcements for the AGM.
Okay, thank you, Jan. Okay, so we have one more public workshop session, which is between the end of the lunch break and the afternoon coffee break at 3 o'clock. We'll be clearing the room at 3 o'clock. The AGM is an OARC members only session. In order to get into that, you need to have a sticker applied to your badge. And that's so we can be sure we've got all the right OARC members. And also, each one of the OARC members, you should have either have sent in a proxy form, or you should have appointed a designated voting representative. If you were the designated voting representative, you need to pick up your voting card. So if you're an OARC member, you're going to the AGM, on your way to lunch, if you can please check in at the registration desk with Sue or Jerry or Dinesh, and they will get the sticker on your badge and make sure that the voting representative has the correct paper. Now, we know it's a Friday afternoon. Some of you have been at NANOG. It's been a long week. But it's important that we make quorum for the AGM. So if you're an OARC member and for some reason you're leaving early because of travel arrangements, please can you make sure that you leave a proxy form for your organization. And that's it, basically. Enjoy lunch, and we'll see you back at 2 p.m. for the final session of the day.